All right, subscribers, welcome back to another episode of Science with Surbeck. Today what we're going to get into is the basics of chemical bonding, and then we're specifically going to look at ionic bonding as one of our types of bonding in a little bit more in depth and in details there. So before we get going into notes, there's a few objectives that I would like to outline before we jump into these details. So objective number 1, determine the number of valence electrons for an atom and write its Lewis symbol. Objective 2, state the octet rule and how it is applied to the valence shell of atoms in a molecule. Objective 3, explain the factors that affect the value of lattice energy for a solid ionic substance. And objective 4, write the valence electron configuration for metal ions, including transition metals and anions. All right, so we start out here with the concepts of chemical bonding, and we need to know about Lewis symbols. So Lewis symbols is just a way that we can write the valence electrons in a particular atom. Now, with valence electrons here, it just looks at the electrons in that outermost energy shell, okay? So we have to take a step back and we have to remember that electron configuration that we've talked about before. Remember, outer energy level is, in other words, the highest energy level. Now, I know the electron configuration can take some time, and if you're not familiar with it, it can be sometimes difficult or frustrating. So what I've done is I have a little bit of a cheat sheet that we can use to be able to identify the valence electrons. So I'm going to transition to a periodic table. Now, this isn't in notes, but you can utilize this periodic table here and follow along with me. So with this, determining number of valence electrons, and maybe I should put this here, VE is going to be our valence electrons. And our valence electrons are going to be really simple. All right, for this first column or group, we're going to have 1 valence electron. For this second column or group, we're going to have 2 valence electrons. Now, we skip over the transition and intertransition metals, and we get to this third set, which has 3 valence electrons. This next group will have 4 valence electrons, 5 valence electrons, 6 valence electrons, 7 valence electrons, and 8 valence electrons. We will get to, in this set of notes, the number of valence electrons for your transition and intertransition metals, but I want you to concentrate on these particular elements, okay? Now, what we have here is the number of valence electrons. So keep this chart handy, or keep that periodic table that you filled out handy as we go and we draw the Lewis structures. Okay, so how we determine the Lewis structures. Number 1, we figure out how many valence electrons we have, which if you just use that cheat sheet we went over, it's very easy to determine that. Then we have to place electrons depicted as dots on each side of the element symbol. So what we do, we write down the element symbol, we figure out how many valence electrons we have, and we put those dots around that element. Now, it is particular to how we put those dots around it. There's 4 sides to the element symbol, and each side needs an electron before we go back and we add doubles, okay? So, in our example here, we have P for phosphorus. If we locate P for phosphorus, we notice here it has 5 valence electrons. So how we would draw the Lewis symbol is we would draw a P for phosphorus. We know we have 5 valence electrons. That's equal to our number of electrons we need to put around our P. And so we do it like this. We go 1, 2, 3, 4. Okay? We have 4 out of the 5. Now, where we put that second that fifth electron does not matter. I'm going to put mine up top here. But you could have just as easily put yours down below or to the left or right. Notice how each side got 1 before we went and we added any doubles. Now, aluminum, Al. We find what group it's in. We say, hey, it has 3 valence electrons. So how we would draw the Lewis structure is we draw the symbol Al, and then it only has 3 valence electrons. Now, again, it does not matter where we start, but remember, each side has 1 valence electron, and we only have 3, so that means all sides don't get 1. Again, very simple. You just need to remember, hey, valence electrons, each side gets 1 before we go and we add doubles. All right? Now, you may be wondering, okay, we put dots around the element symbol. Why? What's the point of that? Well, this helps us identify the number of unpaired electrons. And what I'm going to put under this, or I'm going to draw an arrow to, is unpaired electrons is directly correlated to your chemical bonding. Okay? So this means that the unpaired electrons are the electrons available for chemical bonding. Now, how we get to chemical bonding is through sharing, through giving away or attracting those electrons. And we have 3 simple types of chemical bonds that can be associated with the exchange or sharing of electrons. You have ionic, metallic, and covalent bonds. This chapter, this unit, we're going to focus on ionic bonds. This is going to be our focus, okay? Then later on, we'll move on to covalent bonds. But you can see each of the type of bonds that occur here. All right, moving on here, we get to the importance of this, and that is the octet rule, okay? If you noticed that our noble gases here on this last group on the right have 8 valence electrons. 8 can be correlated to octet. So remember, the noble gases are noble or very stable because they have filled S and P subshells. This is why atoms want to get to 8. If they can get filled S and P subshells, they can be relatively stable. The more stable an atom is, the more likely that it's not going to be reactive. But to get to that point, it's usually going to beg, borrow, and steal those electrons to get to that point here. Now, how they get to those electrons is they form these ions, okay? So ions are charged particles because an atom has either gained or lost an electron. And we have 3 main types of ions. We have cations, which are the positive charges. They lose electrons. Positive charge, lose electrons. Anions, which are negative electrons that gain electrons. Okay, so you have to think opposite. Cations become positive, form a positive, or lose electrons. Anions are negative because they gain electrons. And then we have polyatomic ions, which are a group of atoms that have a positive or negative charge, and we'll talk a little bit more about them. Now, what we can do here is we can utilize our periodic table to determine the charge of an atom when it becomes an ion. So, we get to this. Name of the game is to get to 8 valence electrons. They are going to, atoms are going to, in this case, they're going to gain or lose electrons to get to this point. Now remember, a positive charge means they lost electrons. A negative charge means they gained electrons. And that's all because electrons are negatively charged. So we get to this point where it says utilizing the periodic table and determining the ionic charge. So with the ionic charge, what I'm going to do here is indicate the charge that an atom becomes when it becomes an ion. Now these are the typical rules. There are some exceptions, but anything in this first group will lose one electron and become positively one charged. Now this second group loses 2 electrons and has a +2 charge. Again, our transition and intertransition metals kind of wreak havoc on us. So we skip over and we go to this third group. They lose 3 electrons to become positively 3 charge. Again, lose electrons, positive charge. Now our fourth group here with carbon can either gain or lose 4 electrons. Nitrogen, it is closer to becoming over here to that other noble gas, so it is going to lose 3 electrons and have a -3 charge. The group with oxygen has a -2 charge, and the group with fluorine has a -1 charge. Now, the noble gases do not gain or lose any electrons because they are stable. They have that filled S or P subshell, okay? So that is why I don't have a charge indicated for these particular, this group, okay? So now you're wondering, all right, so why did we do Lewis symbols and why, what's the point of this whole thing? Well, the point is this. We can better understand how an ionic bond is formed by determining this Lewis structure. So we have NaCl. And so what I'm going to do here is I'm going to draw the Lewis symbol for Na and Cl. Remember, each side gets 1 before you go add doubles. And so what happens here when sodium and chloride become charged, they enter into an ionic bond, and what specifically happens is this electron here is transferred. So now when the electron is transferred, you get sodium with a +1 charge, and chloride, because it's charged, will look like this. Now I'm going to show sodium's electron that it donated in red. And because it added an electron here, this becomes an -1 charge. Now, you may be wondering, okay, yeah, sodium just donated one of its electrons to chloride. Why are these things staying together? Well, they're staying together because of the electrostatic interaction. Okay, so again, sodium and chloride. When sodium donates its electron to chlorine, making it a chloride ion, they are staying together because of that electrostatic interaction or interaction of positive and negative charges between one another. Okay, so this is the basic concept of ionic bonding. I donate or I accept an electron, and because I donated or accepted that electron, I form this charge which causes an interaction, electrostatic interaction between these particular atoms. And because they're charged, we notify them as ions. So that is what's happening there on the electrostatic front. Okay, so what we get into now, or what we'll transition to, is these properties of ionic bonds. So we saw the basics of why or how those ionic bonds form. Now we get into these properties, and you can see these properties, but what I want to direct your attention to is this. We just went over one formula unit of sodium chloride. Most of the time when ions form, they're going to do so in multiples. And so what happens is they form this nice block structure, and what this does is it causes a greater electrostatic interaction, meaning plus and minus charges are more or less interacting even more, because now we have multiple pluses and multiple minuses very neatly organized into these types of patterns. Now they don't all form a nice cube function, but they do form this structured and systematic pattern. And so because they form this systematic pattern with that electrostatic interactions, they are able to have a very tightly formed bond, and they form these things called lattices or crystal lattices. And so crystal lattices is just saying, hey, how much energy is it going to take to separate the plus and the minus from each other? Well, now they're interacting among one another, and they are looking like this. And so the electrostatic or the lattice energy is, hey, how much energy does it take to separate this plus and minus charge from groups of atoms that are interacting with each other? Okay, so again, let's sum this up before we move on. The ionic compounds form because one atom either gains or loses multiple electrons, and it forms this electrostatic interaction among other ions. Now, this electrostatic interaction is one that is done so through multiple ions. And so as they form this multiple ion formation, they form this lattice energy that is the energy taken or used to separate these particular ions. Now, as we move on here, we have the basic of how ionic compounds are formed, and we can move on to the more specific details of ionic compounds. All right, so let's get into some other details here of ionic compounds. We got into the details of ionic compounds. Bottom line up front is they will gain or lose electrons, form that electrostatic interaction, and that's how they form that ionic bond. Now, ionic compounds are going to occur between a positively charged cation and a negatively charged anion. There are some exceptions. We're not really going to get down that rabbit hole, but there are some exceptions to this. Now, the important things about ionic compounds and ionic bonds is they transfer electrons. Okay, that's a really important concept that we need to understand. The electron is transferred from one orbital to another atom's orbital. Okay, so you're giving it or you're taking it away. All right, now what we do here is we have to have these lattice structures, which means multiple of those ions are going to interact with one another and form this nice systematic repeating pattern. Okay, now let's go ahead, let's get into some details of formula writing. And this should be review, so I'm going to go relatively quickly. All right, so what happens here? The charge of the cation, the positive ion, is written first, followed by the anion. Now, the ratio has to be equal. So your positive charge must cancel out your negative charge. Okay? So what happens here is this. We essentially swap charges, but what happens is this. With Al3+ and Cl-, essentially you can think about this. I'm going to emphasize Al3+. what we have to do to equal out that 3 plus charge is we have to have 3 minus charges from Cl minus, okay? And that's because Cl minus only has a -1 charge. So when we go and we write the formula for Al, or excuse me, Al3 plus and Cl minus, we would have Al, we only need one of them, and we would have 3 Cls, okay? Now, that might be kind of confusing to understand. So what we can do is we can take the charge number from one ion, and that becomes how many we need. Now, we only need 1 Mg, so we just write Mg. And then over here, we need 2 nitrates. Now, whenever you have a polyatomic ion like nitrate, you put it in parentheses, and then out to the side, you write down how many of that ion we need. So Mg2 plus and NO3 minus would be Mg, parenthesis, NO3, close the parenthesis with a 2 to the outside. Now, when we name these particular ionic compounds, we have to do so in a systematic fashion, just like we did when we came up with those formulas of those particular compounds. So with this, we are dealing with inorganic compounds, which essentially means that, hey, they're not organic, and we are going to name them because they have ions. Now, again, there are a set of rules that we have to abide by when we name the particular when we name ionic compounds. And here are these rules. Number 1, you write the name of the cation first. That's the metal. And all you do is you write the name of the metal. So if you find out, hey, it's on the periodic table, it's written first, just write the name. You don't need to modify it, do anything for that. The only exception of this is transition metals. You need to indicate the charge with these exceptions in mind. Then, step 2 here, you write the name of the anion, you chop off the ending, and you write IDE. However, for polyatomic ions, you just name the anion how it's listed. Now, some people like to memorize how polyatomic ions have their names, and there is a systematic set of rules. I, myself, just like to memorize what is the name of the polyatomic ions. However, there are these set of rules that deal with the number of oxygens in the polyatomic ion, and each of these correlate here. All right. Now, again, I don't like to use these rules. These rules are out here. However, I like to just memorize. My positive cations and negative anions. So again, you need to memorize, you need to have an idea of these plus and minus charges. Notice here that our only polyatomic ion that we really deal with is ammonium, okay? Over here on the anion side, we have a lot more polyatomic ions. This is where we get some difficulties when we name or we write the formulas for each and every compound, okay? Keep these handy, but these do need to be memorized. Let's go over some examples. Again, I'm going to underline this here. Always write cation followed by anion, okay? First, second. Okay, so how we do this, or how I do this, is I first divide the cation from the anion. And so we have this, okay? The cation is divided from the anion, and so we have K2SO4. Now, the K is just a single element. So all we do is we write the name of K, which hopefully you know by now, is potassium. And then we look up SO4. Now, you should have a familiarization, but if you don't, look it up on that chart. You write down sulfate, okay? Well, this becomes, the name becomes of K2SO4, potassium sulfate. Pretty easy. And the reason I did not change the name here is because this is polyatomic, all right? Now that's pretty easy. Now we get down to FeCl3. Well, Fe is the name of, or the symbol for our metal, which is iron. However, is iron a transition metal? Yeah, iron's a transition metal, so that means we're going to have to indicate its charge. Cl is chlorine. However, it is the anion. So remember, we have to chop off the ending of that name, and we have to make it IDE. The other thing we have to worry about is the charge. Okay, so we have 1 Fe times the charge of Fe, which we don't know. I'm going to label that as X, plus the charge of, plus 3 Cl's times the charge of Cl. Now remember from earlier in notes here that the charge of Cl, if I find it in notes here, is given at -1. Okay, so -1. And now this is very important here. The charge of a neutral atom is equal to 0. And I'm going to put this here. This right here is the neutral atom charge. Now, I'm going to simplify this. So we're going to have X plus 3 times -1, -3 equals 0. We solve for X, and the charge for Fe is plus 3. Again, charge of Fe. Now we write that charge in the set of parentheses. So we say 1, 2, 3. We always write them in Roman numerals. So the name of this particular compound, FeCl3, would be iron 3 chloride. All right, so let's go on here. We have a special type of ionic compounds, and those are acids. Again, this should be review, so I'm going to go relatively quickly through this. Acids, they're going to yield hydrogen, right? So hydrogen's going to break off into our formula. Remember from acids bases here that H plus is going to neutralize that anion's charge. So H plus is going to counteract that charge from the anion, all right? Again, let's go over naming some acids. Again, this is review, but you name the acids by doing this. Number 1, you turn to the anion first. And if the anion is typically IDE, you change it to ic and add the prefix hydro in front of it. This is only for a single element anion. If the acid's name or the polyatomic name is 8, you change it to ic. Notice there's no hydro. I changes to os. Notice there's no hydro. Okay, so and then you always make sure that you note it, that there's an acid by writing acid. Okay, so let's try this in our example. We identify that there's an H. That means we have to deal with the acid. NO3, if you look this up on your periodic table, this right here is nitric. And so the nitric in this right here, this would be the nitrate. I jumped ahead of myself here. This would be nitrate. Change this to IC. And so because it's polyatomic, this would just be nitric acid. All right, so now this down here, HBr, is not polyatomic. This means that we write down the name of Br, which is bromine. If it's in a a compound, it would be bromide. Now, from our rules, it says bromide changes to bromic, and you add the word hydro in front. I'm going to add this here, hydro, and then you add acid. So HBr would be hydrobromic acid. Now, let's go backwards. Let's name nitrous acid. Nitrous, okay? OUS. This means that this was nitride. If you look up nitride, it is NO2 with a 1 minus charge. Now, because there's an acid after this, this means that we need H pluses. So we need to say H plus and NO2 minus interact with one another. Again, our charges crisscross and they cancel. So the formula for nitrous acid would become HNO2. This should be review. And so you can look back at the notes on naming particular ionic and covalent compounds for this section. Now, I do want to talk about something that I've skipped over, this entire set of notes, and that is transition metals, okay? So the reason I skipped over transition metals when I talked about the valence electrons and I talked about the charges is because transition metals can't obtain noble gas configuration. And so what happens is they lose those valence shell electrons first before they lose any d electrons, okay? So I want to bring back my periodic table as I'm going over this, okay? Now, our transition and intertransition metals are all going to have 2 valence electrons. But our d subshell kind of wreaks havoc here. Wreaks havoc for what we're about ready to do. And I want to make this here an emphasis because these things have 2 valence electrons. We are going to have multiple oxidation states. So what that means is they have multiple charges, okay? Now, what we get into is this. Let's say, for example, we have iron. And I'm going to write the ground state electron configuration for iron, which would look like this. What happens is this. Iron wants to lose its valence electrons first. So what happens here is that because these electrons are in the 4s subshell, they are one of 2 things. One, they are electrons in the highest energy level. What that means is they are lost first. Okay? So what happens? If we lose these 2 electrons, what we can do here is we can have iron that lost 2 electrons and forms a 2 plus charge. So now its electron configuration looks like this. Now, remember from our business on the electron configuration, d electrons like to be filled or half filled. So what that means is that if we lose lose one electron from 3D, if we lose one electron from the 3D subshell, then this D set of electrons becomes half filled. So again, you're trying to satisfy the needs of those subshells by affecting or exchanging those electrons. So again, if we just lose one more electron, we'd have Fe3+, and the electron configuration would now look like this. So again, it's all because of those D subshells and how they interact and how they're written is why we have different oxidation or different charges for each of those transition metals. All right, so again, the last set here just explains exactly what I said, and that is, again, the D electrons here are affecting us and are resulting in multiple oxidation states or multiple different charges for one single atom. A great example of that is iron. So we'll work more and more with those transition metal ions, and we'll determine why they have more and more oxidation states. All right, so I know this has been a lot thrown at you, a lot of review. Hope you have enjoyed this episode, and as always, make sure you subscribe.